Hi everyone, so we're back with the next video. I'm Adi.
And I'm Sudhi.
So we're going to be looking into clustering for this week, right? So we're going to start with the first video on clustering. And so we're going to run through the three concepts which we need to know for clustering, okay? The first one is information retrieval, which we've been doing all this while, right? So we know what vectorizing does and what it has to do. We know what normalization, and all of those are information retrieval from the text we have. So we already know that. So we're covered on the first point. The next one is document similarity. So we're given two documents. How similar are they? This is such a common question which we have in our heads, right? Given two documents, how similar are they? We're going to go through all of the similarity measures in this video. And for the next video, we're going to jump into all the machine learning clustering algorithms and we'll have a look at it. Okay? So let's start with similarity measures.
So, as we are into text analysis, so we will look into some text similarity measures. Here, text similarity is again broadly classified into two parts, which is lexical similarity and semantic similarity. So, the difference is lexical similarity concentrates more on the lexical part of the text documents, which are syntax or the concept itself, whereas the semantic similarity concentrate more on the grammar or the semantics of the sentence. For our classification, so for our learning, we will be looking into lexical similarity. So lexical similarity is pretty common and easy to use similarity measure. And lexical similarity is again divided into two parts, which is term similarity and document similarity. Term similarity goes with term by term. We check if each term in the document are similar. So it's usually done for a string or a smaller document. And the document similarity is when you have two assignments, and when you want to check if two assignments are similar, then you do document similarity. So now let's look into so term similarity has some of the applications, and there are methodologies that are used in calculating the term similarities, and we are going to look into them one by one. So, and the important application of term similarity is autocorrect. When you're typing and you don't know where I or E could land in, so your computer or your phone suggests you perfect word or a correct word. So that is just measuring the distance between the actual word and the word you have typed in, and it gives you the similar. That's how the similarity basically works. Similarity and clustering.
Really cool, right?
Yeah. So now let's look into some of the similarity measures.
So we're going to start with Jaccard similarity. Okay. So given two documents here, actually, Jaccard similarity is the size of the intersection of words between the two documents divided by the union of all the words, which is the simple all the words of both the documents. Okay, we're pretty simple. We have a simple example here. So sentence one is Ram is John's friend and they are close. Sentence two is Ram and John are close friends forever. Okay, so if we draw a Venn diagram for this, the intersection are all the common words in these two sentences, and this one are the uncommon words which are specific to each document. Okay, so based on this, based on the formula which we have here, so the number of words in the intersection is 1, 2, 3, 4, 5, 6. It's so 6 divided by 6 plus 2 plus 1, which is nothing but 6 by 9, which is 1 over 2 over 3, which is 66%, right? So approximately these two sentences are 62% similar. So this is Jaccard's distance. Pretty straightforward and pretty simple to understand, right? And we're also going to look into code examples, but this time we're trying something different. So we're going to push all the examples to the last. Okay? So that's Jaccard similarity. The next one is cosine distance and similarity. So with cosine distance, we know how to vectorize stuff, right? So basically, having two documents or sentences, we're going to find the angle between the two vectors of these sentences. We know how to vectorize them. We can use count vectorizer or whatever, right? So maybe the first step could be to vectorize them,
Mm-hmm.
and then the second step could be to normalize them, and then the third step would be to find
Yeah.
the angle between these two vectors or
Mm-hmm.
sentences. And so if it's 0, that means they're similar. If it's 90, they're kind of unrelated. But if it's 180, they're completely opposite.
Yeah.
So that's cosine similarity. So when we jump into what, so these two similarity measures are the common ones and the important ones, right? So what are the differences between Jacquard's and cosine similarity?
Mm-hmm.
The first one is that um, Jacquard's Jacquard similarity takes in the unique set of words in the sentences or the document. Cosine similarity takes in the length or the length of the vectors and stuff, right?
Mm-hmm.
And so this means that having duplicates is an important thing, right? So if Jacquard's has will not consider duplicates,
Yes.
because friend and friends and
Because
when
it's a
after
set.
you, yeah, it's a set exactly. So it combines it. So if you don't care about the duplicates, you need to go with Jacquard similarity. But if you do care about duplicates, then cosine similarity is a way to go. That's one of the important differences. And one more is the number of words that. So with Jacquard's, you really don't care if a word is repeating so many times. It's kind of related to the duplicates, but if it's repeating, it wouldn't care. But cosine similarity will care if a word is repeated some number of times. So that's cosine distance and similarity. The third one is edit distance, Levenstein's edit distance. This is also a really interesting one, and we're gonna see a small example here. Okay, so what is edit distance? Given, so we're now jumping into words. Okay, so we're gonna take two words and then see how similar or how apart they are. Okay, so let's take these two words. So before we jump into the words, let's just go through this formula for a second. Okay, so we're gonna construct a matrix. Okay, with word 1 and word 2 here. Let's do that first. Okay, so let's take the word 3 and the word trio. Okay, and we also will have this epsilon conversion here.
It's just null, saying from null how much.
Right, right. Steps. So we have these two here. Okay, so now these two are. So we're gonna construct a matrix, right? So let's have that and that. Okay, maybe I should draw it bigger.
No, just take off the horizontal and vertical.
Okay.
Yeah, that should be good.
Okay.
That's a lot.
Okay. So now let's look into this formula. Okay. So if the two are similar, I'm gonna draw this here. Okay. Going right in the matrix is addition of a letter. Going down in the matrix is deletion of a letter. Okay, and coming from the diagonal is retaining our substitution of a letter. Okay, of a character. Character is a better word. So okay, let's start. Okay, so epsilon is you're having nothing. Okay, so to go from epsilon to epsilon, it's a zero. And so the left is, so the row is what you have, and the column feature is what you where you want to go. Okay, so from epsilon you want to go to epsilon, so no transitions. And from epsilon, from nothing, you want to have a t, a single character, so that's 1. From epsilon, you want to go to tr, it's cumulative. Okay? So from epsilon, if you want to go to tr, it's 2 operations. From epsilon, if you want to go to e, it's 3, and the same thing here. Okay? Yeah. Fair enough. And it's the same for the deletion as well. So you have epsilon, and you want to go to t. So it's, I'm sorry, from epsilon to epsilon is 0. From epsilon to t, you have to delete 1, and then the same thing here, you delete. Okay? So that's our first row and first column. Okay? Now we get into the whole addition, retain, delete. Okay? So this formula, if you can see, we have to, for every change, we have to add a 1
Mm-hmm.
to the deletion, to the addition and the deletion part. Okay,
Yeah.
and add a 0 or a 1 depending on if the two characters are
Yes.
equal,
Equal.
are same,
Mhm.
are different. Okay,
Mhm.
so that's here. Okay, so this is C is the cost here.
Mhm.
So it's 1 if the two letters you're comparing are different. It's 0 if the two letters you're comparing are same.
Same.
So that gets added to the diagonal,
Mhm.
and for the top and the bottom, I minus 1 j, I j minus 1, you just add a 1 irrespective.
Yeah.
Okay? So now let's jump into this example and let's get it done. Okay? So going from t, you already have a t here.
Mhm.
You want to get another t. So there's so you add a 1. So you have a t. You have a t. You want to now get a t. You already have what you want. So you want to go from a t to a t. So there's no difference here. Okay. So that's a 0 there. Okay. And so if you see this, you're taking the minimum of these three values. Okay, so basically you're looking into three directions and you're taking the minimum. Okay,
Yes. Exactly.
so that's a 0. Okay, then you're going from a T to a TR.
Yeah.
Okay, so now you need to add. So these two are different.
Different.
Correct. So now you need to add a 1 to the 2 here. You need to add a 1 to this 0. You need to add a 1 to the 1 diagonal. Okay. So now the minimum will be a 1, which is addition from 0. So that's a 1 now.
Yeah.
Okay. So again, so now we're going from T to TRE. So now that's also one more addition. So that becomes 2. And then you have a TREE, so which is also an addition. So you go to 3. Okay, fair enough. So that's one row, correct? So this is also coming from here.
Yeah.
I'll put the directions here. Okay, so now let's look into TR and T. Okay, so we have 1, 0, and 2. Okay, so the two letters are not similar. So you add 1 to all the three values, and now you need to add. So that will be deleting 1. Correct. So that's that. So that will become a 1 there. So deleting from TR, if you delete a letter from TR, you will get a T. That's the rationale behind, right? Now we have a 0, 1, 1, and so you have both these are same. So you don't add. So the minimum is 0. Okay, and so you keep going. So let's just run through it real quick. So you have a TR, you have a TRE. You're adding 1, and then you're adding another. Okay, so now you have 2, 3, and 1 here. So since they are not similar, you need to add 1. You need to delete to get a 2. And then so now we have a 2, 1, and a 0. You have a TRI and an R. So you delete 1, which is 1. And then now here, okay, let's get to this part. This is kind of interesting, right? So now you have a TRI and a TRE, correct? So when you look into that, we have to now kind of substitute, okay? So what we have to do is, and the letters are not same, I and E are not the same, correct? So now you add 1 to all the three. You add a 1 to 0, you add a 1 to 1, you add a 1 to 2, 1 to 1 again. And now, because of that, you are now going to get a 1 here. So the diagonal now becomes 1 because that's where you start varying. Okay, and then let's continue. So now we have a 1, 1, and a 1, 1, and a 2. So you add, they're not the same, so you add, and it's adding, so it goes to a 2 here. Okay, let's continue here. So we have 4, 3, 2. You're deleting, so that's a 3, correct? And so you're deleting, so you have a 3, 2, 1, and you're deleting again, so that's a 2. And so you have a 2, 1, 1, and that's also deleting, so that's a 2. And then the last one, you have a 2, 1, and a 2. They're not same, so you add 1 to everything.
Yeah.
So that's a 2 right there. Okay? So this last value here, that's your edit distance.
So that's the number of operations you need to.
Exactly. So that's the number of operations you need to go from trio to tree, or the opposite. Okay? So that's really interesting, right? So this is a matrix which you have to build based on the two words you have to find the edit distance. I think we've spent enough time on this. So
Yeah.
why don't we proceed to the next one, which is Hamming distance. What is Hamming distance, Sudhi?
So now we have looked into all the similarities where the length of the word or the length of the string doesn't matter. But here, coming from Hamming distance or Manhattan distance or Euclidean distance, which we are going to look further, uh, they have to have the length of the string equal. That means two strings which you are comparing should be of equal length.
Okay.
Here, Hamming distance is a simple similarity measure, or you can say as a distance measure, where you are going to check one-on-one character with the two vectors and see if they are equal. If two characters are equal, you sum up the two characters, and that would be the distance between the two strings.
Okay.
So that is Hamming distance. And coming to Manhattan distance is similar to the Hamming distance, but instead of matching two characters, here we are subtracting the position, the mismatch position from the original length of the string.
Okay.
So that's Manhattan distance, and a normalized form of Manhattan distance, or the most used distance measure, is the Euclidean distance, which everyone are familiar with. So Euclidean distance also gives us gives us the distance measure, and Euclidean distance is a square of root of the square of the Manhattan distance. So that's the main difference between all three distance measure, and all the three distance measures should have the equal length of the string. So these are our similarity measures.
Okay.
Now let us look into some of the examples and run through the code.
Okay.
So let's go. And yeah. So we'll start with
Okay.
so we are going to start by importing some of the libraries that we require. We don't require spicy. It's not confused. Okay. So here I have four terms: believe, with the wrong spelling,
Yeah.
bargain, and elephant. As you can see here, these three strings have same length, and the fourth one, elephant, is not. And this is normal vectorizing stuff. You can vectorize however you need. Like, it's left to you. Here I'm vectorizing them with their ASCII values. So as you can see here, their outputs are the ASCII values of each character. Again, all these characters are normalized. That means every character is taken in their lowercase order, because we do not care if the letters are capitalized or small lowercase. We only care if they are equal. So we just need to know. So that's why capital B and small b, lowercase b, all are having the same ASCII values. So this is my NP array. And let's first look into the Hamming distance, as we discussed before. So Hamming distance, I'm taking the sum of the two terms if they are not equal. So I'm comparing terms believe and believe, and checking which two terms are not which two characters. I mean, which characters are not equal.
Okay.
So if I run the code with normalization false, I should be getting 2. That means B, as you can see here, ASCII values of these two are different.
Yeah. So 105
and 101, when you compare them,
Right.
they're different.
correct. This one
And
this
that,
one.
yeah,
Okay.
exactly.
Okay.
All right. And when it comes to Manhattan distance, it's it's again everything is similar measure. So here, as you can see, I'm checking the shape of my inputs. If the shapes are not equal, or if the lengths are not equal,
It's not gonna work out.
yeah, it's not going to work out.
Yeah.
So, and having distance returns the absolute value. We are here, since we are taking the difference between the positions. So we are actually taking the absolute value of them,
Okay.
just to be sure, and just to not cancel out the differences. So it's a good thing to always take the absolute value when you are doing the sum. And the Manhattan distance between term 0 and term 2, that means believe and bargain, is 38. So going by these values, as the value increases, that the similarity decreases. So as the value is closer to 0, that means the
There's
the two strings are similar. So in the same case with the Euclidean distance, here, as you can see, it's the square root of the sum of the square of two terms. Again, instead of taking the absolute value, it's better to take the square of the difference between the two values. That means you're retaining the shape of the value itself. So calculating Euclidean distance between the two terms, if the distance is near to 0, that means they are close to each other, meaning the two words are similar. So this is all with the three distances where we were concentrating more on the word length as well. And the further we look into, these are edit distance and edit distance, Jaccard similarity, and cosine similarity. So edit distance here, doing a bit of coding. Do not worry about all these. Yeah, do not worry about
We're
it.
basically constructing
Yeah,
the matrix,
matrix.
and getting the maximum and like.
So here
whatever
I'm
we get.
calculating the cost. As you can see here, if the two terms are equal, the cost is zero,
else
as we
it's
have discussed before.
Yep.
And I'm updating the distance matrix by taking the minimum of the diagonal and the vertical and the horizontal.
Yep.
So, and appending it into the edit distance matrix. So do not worry about the code as such, but as you can see here, when you run the edit distance between believe and believe, where I and E are switched, you see that the distance is 2.
Fantastic.
And you can also check for believe and bar elephant. As I said, you don't need to have both strings equal length.
Yeah, that's
So
a point which you need to remember. So for edit distance, they need not be of the same length.
Yeah. So again, you need 7 changes. You need all changes to convert believe to elephant.
Fantastic. Okay.
And let's go into cosine similarity. And our beautiful sklearn has libraries for cosine similarity and cosine distance. And as we have discussed, the count vectorizer or TF-IDF vectorizer. Here I'm just using the count vectorizer. You can also use the TF-IDF vectorizer. I'm vectorizing 2 sentences, and the AI is our friend, and it has been friendly. AI and humans have always been friendly. So you can do 2 things. One, you can just run these vectorize the sentences as simple as that using the count vectorizer, or you can first or you can also, if you do count vectorizer, it gives you the counts of each word.
Correct.
But if you do TF-IDF,
it directly normalizes it as well.
yes. So here, as you can see, friendly, friend, everything is considered as 2 characters. If you lematize and if you do it properly, you are going to get a better score.
Yeah.
So let me run. So as you can see, it's one-on-one mapping. AI has appeared only once in the whole sentence. So this is the array for my first sentence. This is the array for my second sentence.
Yep.
And when I run the cosine similarity of this array, I get 0.5. That means it is kind of closer to the original sentence,
Right.
but not far apart.
Yeah.
Not so the angle, the value. I don't know what is cos point. What leads to cos point? What leads to 0.5? What angle of cos leads to 0.5? No idea. But the value suggests that it is near.
Correct.
So cosine distance is 1 minus the cosine similarity, which is around 0.49. That again suggesting that the angle, the distance between two vectors are not far apart. It's just halfway through. So Jacquard similarity for the same two sentences. For same two sentences, again you can do the lemmatization and all those stuff. Here I'm just doing the basic split of the two sentences, creating the intersection between them, and then calculating the length, that is the intersection divided by the union, and returning the similarity. The similarity between these two sentences is 0.33. That means closer to the, is
So
it
yeah, if it's closer to 0, that means they are not similar.
not similar?
Yeah.
Okay.
So
Yeah, if you
if both of them are the same, you get a 1.
yeah, you can check that. Yes, exactly. Both of them are same. You get a 1. Right. Let's run this. 0.8. Oh yeah, I'm
friend and friendly.
Yeah, this is why we have to do lemmatization.
Yeah.
1. So both of them are equal. That's why it's 1. So closer to 0, they both are not similar. That's how different Jacquard similarity and cosine similarity.
I like Jacquard the best. I like Jacquard.
Personal opinions. All right. So for this video, we are going to come back with the clustering algorithms for the next one.
Yep.
And
Thank you
for watching. Bye.